Okay, so these I call combo questions since there's a couple of steps involved. Here's the classic combo question. It's called a ballistic pendulum. So you fire a projectile into a pendulum. The collision doesn't take very much time, so milliseconds or something like that. So the objects quite quickly reach a common speed, and then the pendulum swings up. So we're going to realize there's two things that happen here. First of all, there's a collision between the bullet and the ballast, it's called, or the pendulum. And then after that, there's a swing. So it goes from there to here. So then a swing happens. And it's going to reach some maximum height and temporarily come to rest. Now, in the collision, momentum will be conserved. It'll be transferred from the bullet to the ballast, but the momentum lost by the bullet will equal the momentum gained by the ballast. So overall, the momentum of the system will be conserved. In the swing of the pendulum, the mechanical energy of the system will be conserved. So these are the two cornerstone conservation laws in physics. So first of all, we will now do this analysis here. So first of all, we'll start with the collision. So here's the bullet hitting the ballast. That's the before picture. And then after, the two of them are moving together at some common speed v. So we had, well, we'll write out the principle. m1 v1 plus m2 v2 before the collision. Total momentum before will equal the total momentum after. So before, we only have the momentum of the bullet, and the ballast obviously has none. Afterwards, we have a combination of the two masses stuck together. So that's 0.02 kilograms plus 4, moving together at a common unknown speed v. Now, this statement of momentum conservation then enables us to solve for that speed. Okay, so that gives us, for that speed, 0.49 meters per second. Then we apply conservation mechanical energy to the swing. So here we have the ballast moving at that speed we just calculated, and it's going to swing up to a height h, and then it's momentarily going to come to rest. So here's the work energy theorem. So the initial mechanical energy is just in kinetic form. For a pendulum swinging in the absence of air resistance, there is no non-conservative work, so there's no gains or losses of mechanical energy, and at the end it's in the potential form. So this will be a half times the combo mass moving at 0.49 meters per second squared. This will be the combo mass times g times the unknown height. G is 9.80. So solving for the height, we get 0.0126 meters, or about 1.3 centimeters. So that's a typical combo question. Here's another one, this one just in text. So the task is to visualize this, draw a picture, and then think about how you would split it up. In the previous question, we had a collision that conserved momentum, then we had a pendulum swing that conserved energy. So pause the video and sort of discuss or think conceptually about how you'd solve this problem. Okay, so hopefully you've had a thought there now, and this is how we should visualize it. So we start off here, a 5 kilogram mass is at rest on this ramp, and it's going to slide down and contact a 3 kilograms. So here it is at the beginning, and we're told that after the collision, just make this a bit smaller here, after the collision, that the two masses move apart at different speeds. So here they are at the end. So this is after their collision. We don't know what these speeds are. I don't know, maybe like V1 final and V2 final. And in between, there's an intermediate state here, and this is really important. Here, we have to, in our minds, imagine the state where the 5 kilogram has slid down the ramp, but has not yet collided with the 3 kilogram. And so the reason that we need to imagine this in our minds is there's two processes here. There's a slide, which is going to conserve mechanical energy. So as the 5 kilogram slides down, we're going to see a transformation from potential energy of the 5 kilogram to kinetic energy of the 5 kilogram. And it hasn't even contacted the 3 kilogram mass yet. Now, then, after that slide, then we're going to have a collision. And then we know that collisions for a closed system conserve momentum. So m1v1 plus m2v2 initial will equal m1v1 plus m2v2 final. And I'm clearly going to run out of room there for that. Conservation principle. So the 5 kilogram has momentum, and the 3 kilogram doesn't. And then afterwards, they're moving apart, and we don't know their speeds. But this would be the correct application of the momentum principle. So there's two steps here. You have to analyze the slide, and then using energy, and then the collision using momentum. Now, a common mistake would be to say that the potential energy here at the beginning, so let's make a note here. Note, the PE of the 5, note, that's a 5. PE of the 5 kilogram does not equal the final kinetic energy of the 3 and the 5. Does not equal this. Why? Because mechanical energy was lost in the collision. It was converted to thermal energy. Collisions in general do not conserve energy unless it states explicitly that the collision is elastic. So it would be a mistake to say that the energy in this picture equals the energy in this picture. Instead, we have to analyze first the slide using conservation of energy, and then the collision using momentum. Here's a similar question. There's 3 masses. They're going to hit and stick. Stop the video, then think about how you'd analyze this problem. How many steps are there? Which principles will you apply, and in which order? Okay, so hopefully you realized that there's sort of 4 steps here. First of all, these 2 masses are... Okay, so the first thing that happens is these 2 masses collide, and they stick together, and then they move away at some common speed v1. So momentum is conserved. So sum of the initial momentum equals sum of the final momentum. So using the variables on the picture, we have m1v of momentum plus that mass which is at rest. Then the 2 objects are stuck together and moving at speed v1, still along the lower surface. Well, then what happens is they slide up this surface to some height h. This will be mechanical energy principle. Now at the beginning, we've got the kinetic energy down here at the bottom. There's no gains or losses in mechanical energy. Up at the top, it's going to be moving slower because it's gained some potential energy. So here at the bottom, we had the combo mass moving at speed v1. Up at the top, we're going to have the combo mass moving at this new speed v2 squared. And then we're going to have the combo mass gh. I just don't have enough room for m1 plus m2 there. So because there's been a gain of potential energy, there'll be a loss of kinetic energy, and v2 will be a little slower. So then these 2 masses are going to collide with mass m3, and that collision will conserve momentum if it's done in a closed system condition. So the momentum before the collision is these 2 moving together at speed v2. Then this mass has no momentum, so if you like, there's a plus 0 there. And then after the crash, all 3 masses are moving together at speed v3. Now we don't have any values for any of these quantities, so we can't actually work anything out, but we can say that first we have a collision that conserves momentum, then we have a slide up a ramp that conserves mechanical energy, then we have another collision that conserves momentum. So there's 3 analysis steps here. And so that's an introduction to combo questions, and you can see there's a little bit of an art to knowing how to split them up, and we'll work on some of these in class together tomorrow.